So in the last video we introduced independent events. Alright, what the difference between independent events and mutually exclusive. And so in today's set of notes is we're going to look at a bunch of examples and we're going to test to see if they are independent or mutually exclusive. Basically it's the independent test. While I'm doing the independent test, it'll fall out whether or not they're mutually exclusive, whether the and statement is 0 or not. Alright, so testing for, remember when we test for independence, we're testing if the condition matters. So the test is, if I find the probability of an event, is it the same or different, right? Is it equal to or not the probability of that same event given a different event? Alright. So we test, is event E, is the probability, the general probability of event E out of all outcomes, that chance, that percent, decimal, fraction, the same or different, so really this is a question mark, is this equal or not equal to that same event given another event? Alright, so is event E given T the same as event E? If they're equal, so again that's what we're testing, we don't know, that's what we're checking to see if those are equal or not. If they are equal, it's independent. If they are not equal, they're dependent. The condition matters. Alright, so that's the test. The test for independence is checking, does the other events, if it was the condition, does it matter? Alright, or not. Right? And then the mutually exclusive part, mutually exclusive, is the number in event A and B 0. Alright, remember, if there's 0, mutually exclusive, which will fall out of this statement because my and statement shows up here. Alright, so if it's 0, yes, mutually exclusive. If it's not 0, no, it's not mutually exclusive. Alright, so those are the tests that we're going to do in this set of notes. Right, we're going to do a basic example, a standard deck of cards, which I've given you the standard deck, other than it's not colored. Remember, the hearts and diamonds are the red cards, and the clubs and spades would be the black cards. Alright, so my events, A is the event of drawing a diamond, B is the event of drawing a jack, C is the event of drawing a black card, so a club or a spade, D is the event of drawing a face card. Remember, face cards are our jacks, queens, kings, alright, so J, K's, and Q's. So the first one is A and B, so I'm just looking at events A and B, alright. Is the event of drawing a diamond independent of the event of drawing a jack? Is the event of drawing a diamond mutually exclusive? And you can probably answer that one right away. No, they're not mutually exclusive because I can draw a diamond that is at the same time a jack. So the and statement's not empty. Right, but the independence is not as easy. Right? I don't know if it's a yes or a no. And so remember, when we test, the test is, well, we pick one of them to test. I'm going to test A. You could do it the other way around if you want to. You could test B. What I'm going to see is the probability of A the same, equal to, the probability of A given the event I'm testing it against. So I'm testing it against B, so B is going to be my given event. Are those two probabilities equal? If they're equal, yes, they're independent. If they're not equal, nope, they're not independent, they depend, the condition matters. And then we just find them. Remember that the universal set would be the number in A over the number in my universal. Is that the same as the conditional formula, which is the given event, right, and divide by the number in B. Up top is the and statement, which this is where the mutually exclusive will fall out. Number in A and B. If that's 0, they're mutually exclusive. If that's not 0, anything but 0, then the answer is no to mutually exclusive. Alright, so A is the event of drawing a diamond. So remember, there are 13 diamonds out of my 52 cards. So the probability of getting a diamond is 13 out of 52. Is that the same as the condition, which would be given that I drew a jack, so number of jacks is what I divide by, so there are 4 jacks, right? Out of the 4 jacks, I then want the number that are both jacks and a diamond. Well, one of those jacks is a diamond, so one of the 4 is. So is 13 out of 52 the same probability as 1 out of 4? The numbers are different, but is the probability the same? And it is. If you divide this out, that comes out to 0.25. You divide 1 and divide by 4, that also comes out to 0.25. So yes, there is a 25% chance of getting a diamond if I have the entire deck of cards. And there's also a 25% chance of getting a diamond if all I have is the 4 jacks. And that one's probably easier to see, right? If I've got 4 jacks, one of them's a diamond, so I've got a 1 in 4 chance, which is 25%. What's the same ratio of diamonds if I've got the entire deck? 1 in 4 of all of the deck are diamond, right? 1/4 of the deck is diamond. So there's a 25% chance of getting diamonds. And so since they're equal to, that checks, right? They're equal to. That means that, yes, A and B are independent events. Right? The condition didn't matter. So yes to that. No to mutually exclusive, because this does not equal 0. It equaled 1, right? Number in A and B was 1. Well, 1 is not 0, right? 1 does not equal 0. And so, no, they are not mutually exclusive. Alright, so part A, yes to independence, no to mutually exclusiveness. So we're basically the same thing for B, but we're going to pick 2 different events and test to see if they're independent or mutually exclusive. Alright, so now again we're looking at B, event B and C. So we're going to test to see if B and C are mutually exclusive or independent. And so the test, remember, is I test to see, does the condition matter? And you can start with either event. You could either pick C or you could pick B. It really doesn't matter. I usually just pick the one that's the start. So I'm going to check the probability of B against the probability of B given the other event, right? Does the other event matter? Does it affect the probability of B? So given C. And so I'm going to find my universal probability for B. Is it equal to or different than the conditional probability? The condition C. So it's out of all my C events. How many ways does B happen? Alright, so B is the event of drawing a jack. So there are 4 jacks out of my universal set. So 4 out of 52 for the universal case. Right, is that the same as my condition? Alright, so the condition is I'm drawing a black card. So the black card are just the clubs and spades, right? Those are the ones that are all black. That's event C. Alright, so half the deck would be 26. Out of the 26, how many ways can I draw a jack? Well, there's 2 jacks that are also at the same time black. So 2 out of 26, and it should make sense. If I have the full deck, and I'm drawing a jack, I had 4 outcomes out of all of my deck. If I have half the deck, I have 2 outcomes, which are half the number of jacks. And so those come out the same. If you divide them out, it's the same fraction. Right, if I round a couple decimal places, it's 0.0769. Well, the same thing here is when I take 4 divided by 52, is 0.0769. And so that checks. If I have the entire deck, I have almost an 8% chance of getting a jack. If I have half the deck, I still have an 8%, almost an 8% chance, right? A 7.69% chance of getting a jack. So it didn't matter if I had the full deck or half the deck. I had the same odds, the same probability of getting jacks. So long as the half the deck is split into 2 suits, right? Jacks, or the black cards. And so the answer is basically the same as I had before, the same one. So, yes, so for this one, yes, B and C are independent. Alright, the probability of B did not change given C, so the probabilities were equivalent, whether I had the whole deck or half the deck. And the answer to mutually exclusive is no, because there were 2 events they shared, right? That is not 0. And so, not mutually exclusive. mutually exclusive. My pen battery is dying. It's not working as well. Alright, I digress. Alright, so next example, same song and dance. Right, this one I believe does have different outcomes. I believe the next two have different outcomes. And basically, I'm going to hit all of the cases that you can have. You can have yes independence, no to mutually exclusive. You can have no to independence, no to mutually exclusive. You have no, and you can have no yes. You just can't have yes. You can't ever be mutually exclusive and independent at the same time. Not possible. So you can either have two no's, one no and one yes, right? But you can't have yes to both. All right, so the next one we're looking at is A and C. So my test, all right, is the probability of A the same as the probability of A given C. So again, it'd be the universal case versus the conditional case. Oops, I put B instead of universal. Universal. Alright, then the conditional case, the condition is C, and then the and statement. Alright, that's the conditional formula. Alright, so this was the diamond case. 13 out of 52 are diamonds. Is it the same as... Well, remember, C is the black cards, the spades and the clubs. Right? That's what C is. C is this. So, if all I'm giving you, if I hand you just the spades and the clubs, alright? These are the black cards. That's my C event. So if I already have given you just that half of the deck, and then I ask you, well, if I'm giving you the spades and the clubs, what's the probability I get a diamond, right? Because the B event is getting... Sorry. The A event, not the B event. The A event is getting a diamond. Alright, I'm going to double check before I say that. Yes, A is what I'm looking for. So if I'm giving you the half of the deck, the 26 cards that are black, that are spades and clubs, what's the probability that I get a diamond? Remember, A represents diamonds. Well, if I didn't give you any diamonds, there's no chance of getting diamonds, right? If I have the black cards, diamonds are red, there's no way to get a diamond if all I have are the black cards. And so this is 0, right? There's a 0% chance. There's no overlap. The and is empty. If I have the black cards, I can't have a diamond at the same time. I can't pull a diamond out. And so that's 0. And so this time they don't match, right? Those are not the same. And so the answer is no, they are not independent. They're dependent. Yes to mutually exclusive, right? And so they are not independent. Right? Because those don't match. And because the number in A and C is 0, yes, they are mutually exclusive. So, no to independence, yes to mutually exclusive. Alright, so again, not independent, because if I don't have, it matters, right? If I have the black cards, there's no way to get a diamond, so it mattered. That event mattered. Cutting the deck in half between black cards and red cards affected the outcome of getting a diamond. And it basically made it impossible to get one. Alright, so when I have mutually exclusive events, they can't be independent. Alright, so that means this is the no-no case, right? Neither one of these can happen. But we'll test it and show that that is the case. So I already kind of given you a heads that no, they're not going to be independent. No, they're not going to be mutually exclusive. And we'll test to show that that is the case. Alright, so find the probability of D. Is it the same as the probability of D given my other event, which is B? Alright, so it's the number in my universal set. Number of D events out of my universal. Is it the same as the condition? Number in my given, which is B, out of my universal, which is D. Alright, I don't remember what D is, so I'm going to have to go look. Alright, so the D is the event of drawing a face card. Alright, so D are my face cards. Alright, so that's event D. So there are 12. Alright, those are the 12 face cards, jacks, queens, and kings. Alright, so there are 12 possibilities out of 52 to get a face card. Is that the same as the outcome if I have B given D. Alright, so B, I've got to go remember what B is. Alright, so B is the event of drawing a jack. Alright, so that's event B, drawing a jack. So if you're holding the jacks in your hand, right, if you've got the jacks in your hand, what's the probability you get a face card? Well, this was kind of one of those head scratchers cases, right? If I've got the jacks, that's what B is, right? So there are 4 jacks, right? B is the jacks. D is my face cards. So again, the conditional event is I've given you the 4 jacks. So you're holding the 4 jacks. That's it. That's the only part you have. So that's the condition. You're given that I'm holding the 4 jacks in my hands. Well, if I'm holding the 4 jacks in my hands and you draw a card, what's the chance it's a face card? Well, all of my jacks are face cards, and so there's a 100% chance all 4 jacks are face cards. So there's a 4 possibilities out of 4. So that's a guaranteed probability. It's one of those. Remember, 1 is a perfect. We don't get them very often, but 1 means it's going to happen. If I have all of the jacks in my hand and you want a face card, well, you can draw any of the jacks and you're guaranteed you have a face card. Alright, so those are not the same because that's 1, and that obviously 12 out of 52 does not equal 1. And so, no, they're not independent because that's not true. And they're also not mutually exclusive because all of my events in D are shared with B. And so my AND statement, which I didn't write here, this was my AND statement. Sorry. My conditional event, that should have been my AND statement. My AND statement was 4. Right? They shared all 4 outcomes in D in common, right? That's 4, which does not equal to 0. And so the answer is no to both of them. They are not independent, and they are not mutually exclusive. Alright, so no to both. And so those are the only outcomes you can get. No to both of them, or no to one of them. Either it's no to independence, yes to mutually exclusive, or the other way around, no to mutually exclusive, yes to independence. And that's the only outcomes that can come out when you're testing for independence and mutually exclusive events. Alright, so again, those are the only possibilities. So on your own, test to see A and D, so I should have said on your own. Check, and so your test is going to be, you're going to test, you can test however you want. You can take the probability of A, is it the same as the probability of A given D? Is that the same? Or if you prefer the other way around, you only have to do one of them, but if you want to be on the extra cautious side, you could do both. Probability of D, the same as the probability of D given A. Are those equal to or not? Alright, and check to see if they are. Alright, so I'm going to leave that for you, and again, like I said, I'll post the answer sometime later in the week. But do try that on your own, and we'll stop the video there and pick up the next set of notes. There should just be one video left, which is just practicing applications where they're going to tell you, so you don't have to test for independence in the next set of notes. We're going to go ahead and tell you they're independent, and you're going to use the fact that they're independent to solve the probabilities, and we'll do that in the next set of notes.